In this talk, we are going to be looking at a method that has come to be known as optimal interpolation. I would like to provide a quick historical perspective of this approach to prediction estimation based on a method that has come to be called optimal interpolation. During the 1960s and 70s, operational centers in USA, Sweden, Japan and others routinely used iterative scheme like Berthorsen, Dew's or Cressman type that we talked about in the last lecture. These methods have also come to be known as successive error correction. You can see Z minus h of xk in the iterative scheme, which we can think of as an innovation, is also can be thought of as error, and by iteratively performing the update, we are trying to transfer the information from the observation network to the computational network. So that method, that class of methods, Cressman type schemes, have also come to be called successive error correction method. When this was going on in USA, Sweden, Japan and other countries, in Soviet Union in 1960s, a technique called optimal interpolation was championed by Gandin, Lev Gandin. Optimal interpolation was developed earlier independently by Norbert Wiener around 1940s in the USA and Kolmogorov in the Soviet Union. The story goes that Norbert Wiener developed this method in the early 40s, but he did this work under a defense contract. So it was classified, and by the time he could publish it, it has to be unclassified. So it took several years before the first classification of Wiener's ideas were known to the public. So the publication date, the open publication date is around 1949, but he had also independently developed in the early 40s, not knowing that Kolmogorov was also working on similar problems. This goes to show big minds think similarly, even though they have been working in geographically distinct locations. What is the basic idea of this method called optimal interpolation? I am going to illustrate this notion of optimal interpolation using a simple 2D grid problem. It can be extended to 3D grid as well. Consider a 2-dimensional grid with nx times ny number of points. Nx is the number of points along the x direction, ny is the number of points along the y direction, n is the total number of grid points. Let there be m observations inside this grid space. As an example, I had nx is 4, ny is 4, so n is 16. I have a set of 5 observations z1, z2, z3, z4 and z5. We can think of these observations as scalar observation, temperature, pressure, humidity or concentration of some chemical, whatever quantity of interest, but essentially it is a scalar. So I am now going to consider 2 cases in our illustration. First, let us assume the observations are perfect. Observations are perfect means there is no noise. Why do we do that? Even though we know observations generally are associated with noise, I think it is good to get a grip on the idea by assuming that observations are perfect. So the field variable of interest, as I said, is a scalar field variable. It could be temperature, pressure, etc. Consider a time k, noon January 1st 2016 as an example. So k is a specific instant in time. There are m observational occasions. So at that time k, there are m observations of the scalar field variable, temperature, pressure, whatever, and I have a m vector. The components of the vector are z k1, k2, km is a m dimensional vector at time k, zk. These are the observations that are available from the m observation stations. Now the observations that we are concerned with has a natural variability in itself. For example, if you consider the temperature at the downtown Paris on January 1st of every year, there is a natural variation. The no two successive years will have exactly the same temperature in downtown Paris at noon time on January 1st for the 100 years. So you can think of these scalar variable to be naturally varying. This natural variability is captured or is described as a random process. So given this natural variability, we are going to consider zk as a random vector. So zk is random not because of the observational errors, zk is random because of the inherent natural variability resulting from changes that are inherent to climate variables. It is assumed the observations are error free. That is what perfect observations relate to. So the whole method of Wiener and Kolmogorov, which has come to be called optimal interpolation, rests on the assumption that the properties of the random vector zk is stationary. What does it mean? The random process that describes the temperature time series is I'm sorry, that's correct, has a stationary distribution. So what does it mean? Z is a random vector. Every random vector has an associated probability distribution. If that probability distribution is invariant in time, that is called a stationary distribution. If that probability distribution changes in time, it is called a non-stationary distribution. A fundamental assumption is that the temperature in downtown Paris at noon on January 1st of every year is drawn from a stationary distribution. The stationary distribution is the one that describes the underlying natural variability. So given this stationary distribution that is behind the realization of zk, z bar is the mean of z, z tilde is the anomaly, z minus z bar, expected value of z bar is 0, the covariance of z is given by expected value of z bar transpose, and that I am going to call it C. So C is a m by m matrix. C matrix talks about the covariance of the observations from different locations. It is assumed that both the mean and the covariance of the observations are known. So let us go back. In this case, I have a grid with 16 points. I have 5 observations. I am now talking about observation vector. So let us fix the time, so I do not have to worry about k. Let us fix the time k to be noon January 1st. So at noon January 1st, I am getting 5 observations. Z is equal to Z1, Z2 up to Z5. This will have a mean Z bar, This will have a covariance matrix C. The covariance matrix C will consist of Cij. I runs from 1 to 5, J runs from 1 to 5. What is the meaning of Cij? Cij is the correlation between the scalar variable at location I to the location j. So in order to be able, so it is assumed that this correlation is known. That is the key to the methodology. So the whole question is this: we assume the distribution is stationary. We may not be able to get a handle on the stationary distribution, but what is that one can do? I should be able to estimate z bar and C. How would you estimate z bar and the covariance Z? So let us look at the station. So let us take the time series of observations. So Z1. So if I now consider the time, if I bring in the time now, Z becomes a Zk. Zk is equal to Zk1, Zk2 and Zk phi. Therefore, if I consider station 1, I am going to have a time series of that measurement over a long period of time. So we are, for example, I am trying to measure the temperature in downtown Paris at noon every day. So that time series is known. So once that time series is known, so what is that we are going to assume? I am going to fix the location downtown Paris. I am going to fix a particular instance in time, namely noon of a given day. So every day in downtown Paris I am going to measure the temperature, and there is a record of it, and that time series is made available to me. That time series is a long time series. Likewise, so downtown Paris is only one observation station, and I picked for an example. In this illustration there are 5 such spatial observation towers or observation locations. From each location at each instant of the day, at each hour of the day, there is going to be measurements of the scalar variable of interest. So these sensors are going to spit out the values of the observed quantity, and I am assuming I have already recorded. So that is the fundamental assumption. So given a long time series of observation from each of these locations, I can now compute the mean. So I can say downtown Paris, what is the mean? So what is that I need to consider? What is the mean temperature in downtown Paris on noon January 1st? What is the mean temperature in downtown Paris on noon January 2nd? So day by day, by processing the data, I should be able to compute the mean. Once I compute the mean, if I have time series, I should be able to compute the anomaly. Once I compute the anomaly, I can compute the variance of the measurements at a given location. This I can do for every location. So I will have m locations. For a given time I will have m means, I will have m anomalies, I have a time series of anomalies. Using the time series of anomalies, I can also now compute the covariance. So how do I compute the covariance? Let us say Cij. Cij is equal to, let us consider, I'm fixing the time right now. So time k is fixed. So I have an anomaly at station I have a time series of that with respect to k. So Zi tilde k is the anomaly at the kth instant in time at the ith station. Zi tilde, these are scalars. I do not have to have even written like this. I simply can square the anomaly. One second. I can square the anomaly. Sorry. I can square the anomaly. I can sum this anomaly over k is equal to 1 to n. I can compute by this, and this will give me this is not ij, this is ii. So that is the variance at a given station. Now I would like to be able to compute the elements Zij. This is essentially equal to Zi tilde at time k, Zj k tilde, the product of the anomalies at station I and j. I am going to have to sum this up over k is equal to 1 to n over n. So this is an estimate of the covariance between station I and station j. This is the variance of the station I. These two together decides the elements of the covariance matrix C. So what is the fundamental assumption? There are two key assumptions that are here. I am assuming the scalar field variable of interest, such as pressure, temperature, whatever it is, has a natural variability. This natural variability can be captured by a stationary distribution. Why stationarity in distribution? Analysis of non-stationary stochastic processes are extremely difficult. There are very few results in the analysis for the analysis and quantification of properties of non-stationary stochastic processes. The only thing we know is to be able to pin down, analyze, characterize the properties of stationary stochastic processes. So in here Zk is the observation vector at time k. It is said to arise out of a under assumption is said to arise out of a stationary distribution. Stationarity is fundamental to anything that we can do computationally. That is the fundamental key. So it is the limitation that is imposed not because we want it, but because if it is not stationary, there are not too many things we know how to do analytically. So stationarity assumption is fundamental in almost all of the time series analysis, and likewise here I am assuming that I'm having a parallel time series at each of the m locations, one for each station. From each of these parallel time series I can now compute the statistics, the individual mean, the mean vector, the individual variances, the covariances. These two together summarize the vector z bar and the matrix C, and that can be done if you give me a long series of time series at various stations. So we assume that we have availability of z bar and C at m stations. So that is what exactly is what I described is now reinforced in this slide. Let me quickly reinforce that. So computation of the spatial covariance, C is the computation of spatial covariance among m observation stations. Z is the time series of the field variable, z bar is the vector of means. So I am now doing, instead of doing individual stations, I am collectively doing for all stations. Zk is the vector, z bar is the vector. I am trying to take the average of capital T number of observations. Z tilde k is the vector of anomalies. Earlier I talked about the individual anomaly, now I can collect them in the vector. It is a vector of anomaly. If the vector of anomaly is known, I can now compute the covariance matrix as z tilde times z tilde transpose the summation over k 1 over k. This C is symmetric positive definite. That is the assumption. Why? If the number of samples is large, if the number of samples has been collected over a long period of time, I think one can readily see this C covariance. The covariance is always symmetric. If the number of data is small, it may not be positive definite. If the number of data is large, there is a reason to believe that C so computed would indeed be symmetric and positive definite as well. So I am going to make an assumption that C is symmetric and positive definite given. So what does C captures? That is the important thing. That is the fundamental idea of both Kolmogorov and Wiener, and they proposed this in early 41-42. The matrix C captures the natural variation in the observation, natural spatial variations. Please remember, this is not related to the observation error covariance. I should have said error here, observational error covariance. Observational error covariance is R. In this case R is 0 because we have assumed the observations are perfect. So this spatial covariance essentially captures the natural spatial variability of the field variable of interest in the region covered by the in the geographical region covered by the M observation stations. That is the fundamental idea. That is the starting point. Now let me go back and talk about why are we interested in this correlation. Please understand, our ultimate aim is to predict. To predict, I need to assimilate. To predict, there are only two kinds of things you can bank on to be able to generate a prediction. One is causality, another is correlation. So if you are trying to use models to predict, the models represent the causal relation that exists and that helps to describe the underlying physical process. For example, the dynamical system that relates to the motion of the earth around the sun, the dynamical system that relates to the motion of the moon around the earth. This combined dynamical system we have understood very well, and using it we are able to predict the lunar and solar eclipses to very high degree of precision. So this dynamical system essentially has captured the causality principle that underlie the motion of the moon around the earth and the earth around the sun. So likewise, every model, be it static, be it dynamic, be it deterministic, be it stochastic, all models in some sense encapsulates some form of this causality principle. Momentum is conserved, energy is conserved, these are all causality principles. In the case of time series, I derive empirical models, autoregressive moving average models. They are empirical models. These empirical models in time series are essentially derived out of correlation. So what is that we do? We look at a time series, you compute this temporal correlation. We see how the temporal correlation decays with time. If it decays fast, the process has less memory. If it decays very slowly, the process has long memory. Mathematicians have already analyzed properties of several different types of time series models, and they have catalogued and they have created an album, if you wish, of correlation structures of various models. So given a time series data, you compute the correlation structure of the given time series and compare it against the album and look at which one looks closest. It may not be 1, it could be a subset of 2 or 3. You narrow down the window and then try to use each one of these models to be able to distinguish which model is better. So what is the underlying theme? To be able to predict, either you need causality or correlation. This approach to optimal interpolation rests on our ability to predict based on correlation. So what does it mean? If two quantities spatially separated is positively correlated, means what? If the variable in one of the stations increase, there is a likelihood the other station will also increase because there is a positive correlation. If there is a negative correlated, if one increases, the other will decrease. So I can infer from the increase or decrease of a particular quantity in a given station, and knowing the correlation, I should be able to predict what will happen at the other station. That is the fundamental principle that underlie predictive science based on correlation. So fundamentally, ultimately the aim of data assimilation is to predict. Data assimilation essentially tries to help you to fit the model to data. Fitting model to data is essentially model calibration. So the forecasts generated from calibrated models are better than the ones generated from uncalibrated model. That is why we do data assimilation. The alternative to that is to be able to understand spatial and temporal correlation structure. Wiener's theory applies both to temporal correlation analysis as involved in time series analysis, as well as spatial correlation analysis as would be of interest in any geophysical science. So the matrix C captures the natural variability of the variable of interest in the chosen geographical domain. Now, so I have, please go back to my original picture here. I have a grid, I have an observation stations. So the C is the covariance among the observation stations, but my interests are in computational grid. For example, if I have established an observation network, the observation network is going to be fixed in spatial distribution. Computational grid, depending on the computing power, I can change the computational grid at will. If I have a larger computing power, I can have a smaller grid size and a larger grid number. If I have a smaller computing power, I may have a coarse grid and a smaller total number of grid points. So computational grid, there is no fixed value for that. It depends on what else I am interested, what kind of processes I am interested in analysis and so on. So now what is that we would like to be able to do? We would like to be able to transfer the knowledge from observation network to the computational network. That has been the theme in the successive error correction that we have been talking about in the last lecture as well, iterative methods. So the theme is very similar, except that this new idea is rooted deeply in the correlation structure. So if I have values in the observation network, please recall our ability to transfer information from observation network to the grid network. This is Rm, this is Rm, this is Z, this is H, this is H transpose. This is H transpose. So I can go from one network to another network by this interpolation scheme. So what is that we have done? From the observation stations, we can also think of having a time series of values at the grid point using this interpolation. So if I have a time series, so let us fix a particular time, noon January 1st, I have m stations, I have a H matrix that can interpolate between the computational grid and the observation network. Yes, you may say, hey, if you interpolate it, is not the interpolation is going to incur error. Yes, it may. I am cognizant of that, but I want the reader to appreciate that I have the ability to lift the information from one network to the other network through H and H transpose. So let us pretend now I have a corresponding time series of the same physical field variable of interest at each one of the n grid points. The time series is the same. In other words, at noon I have an observation station, at noon I have interpolated value along the grid. Noon of today, 2 o'clock of today, 5 o'clock of today, every day. So by hour I have a time series going over, let us say, 50 years of data. I can do that. Again, I want you to recognize, while the observation network is fixed, the computational grid may be changing. So if I fix the computational grid, and if the computational grid embeds the observation network, there is one way to be able to lift it from the observation network to the computational grid. So once I have the same time series at the computational grid, I have a vector x from the vector z. This vector x, it belongs to Rn, vector z belongs to Rm. If I have a time series on the grid, I can compute its expected value. Then I can compute the anomaly. The anomaly is such that its mean is 0. Now comes the important thing. Let D be a matrix that captures the cross correlation between the grid variable and the observation the grid and the observation network. So x tilde is the vector that is defined on the grid. X tilde is the vector. So X tilde is a vector belonging to Rn. Z tilde is a vector belonging to Rm. So if I multiply X tilde by Z tilde transpose, you can think of this as this is the column, that is the row, there is an outer product matrix. This matrix is going to be Rnm. If I took the expectation of this outer product matrix, that is D. So what is D? D is the n by m matrix that relates to the cross correlation between the grid variables and the observation variables. So this is the cross covariance between grid values and the observation variables. So C and D are going to play a very major role in our analysis. Now please remember, C may be fixed in time because observation network, once we establish a network, we can't change, but D can change in time. I am sorry, the computational grid can change in time, N can change in time, therefore D can change in time. So how do you get from observation to C to D? Is to be able to interpolate from observation network to the grid network. This interpolation scheme, there are several such schemes. I have already talked about a bilinear interpolation that interpolates between grid and the observation network. So we can use one of many. So what is that? So what is that we have? I have access to C, now I have access to D. C is the covariance of the given field variable of interest at the observation location. D is the cross covariance between the grid and the observation network. So you have, there is a lot of statistical computation. So if you have a time series over 100 years, if you have a time series over 100 years, hour by hour, minute by minute, your data set may be very large. From that said data set, you have to crunch the value of the matrix C, you have to crunch the value of the matrix D. That can be done. Very routine calculation, it does not take too much time. Here I am just trying to describe formally the notion of computing the elements of the matrix. I want to reinforce that again. So let us quickly run through these calculations. Let xk be the state variable vector of the same field variable at the grid locations at time k. We may have a time, so if Z has a time series, there is a corresponding time series for X. Once I have the time series, I can compute the mean, I can compute the anomaly, I can compute the cross product, which is D. That is what, so there we talked about the concepts, here we talk about algorithms. So concepts, algorithms, algorithm for C, algorithm for D are given. Now what is the statement of the problem? I am sorry, there is a spelling problem here, there has to be a T. Let the observational covariance C and the cross covariance D be known, matrix C and matrix D be known. So what is C and D represent? C and D represents the stationary values of the covariance between observations and covariance and the cross covariance between observation and the grid. Because the underlying processes are stationary, C and D does not change in time, especially C and D does not change in time if you consider a long time series. And so what does stationarity means? I want to comment on that a little bit. If the regime of the climate has changed, the underlying distribution would have changed. So what does stationarity assumption means in practice? We are assuming the regime under which the climate is operating has not changed statistically. That is the idea. So how do you know the regime we are operating has changed or not? That is a different question. We should have a long time series. You should break the time series into different parts. We should calculate different quantities in different times, and see whether these statistical quantities has changed over 100 years. First 100 years, second 100 years, third 100 years, first 50 years, second 50 years, first 10 years, second 10 years. So decadal variation, century variation, annual variation. So one can do statistical tests for regime changes, regime shifts, if one has access to a reasonably long time series. In other words, one can test the hypothesis, namely if the underlying statistics is invariant or changing. So it all depends on how much data you have. If you don't have much data, you can't even do that testing. If you don't have much data, if you can't do that testing, just pray the Lord and assume it's stationary. So these are some of the key things that one has to keep in one's mind. Now, so what does CND refers? In some sense they refers to the climatology, and that's the important thing here. CND refers to the underlying climatology, the stationary aspects of the climatology. Suppose a new year dawns, January 1st, 2016, today. I have computed CND over the past years. A new observation from my observation network arises on this new day. These Z observations are available only in the observation network. But I would like to optimally compute the values induced on the grid X. So I hope you understand what I'm talking about. CND are known. CND are based on the past values. They represent the climatology. A new day dawns. A new day brings a new observation Z. The new observation C is confined to observation location M of them. But I would like to be able to elevate that M to N grid points. How do you do that? How do you do it optimally? So that's the statement of the problem. Given a new observation Z and the climatological information embedded in CND, how to optimally compute the induced grid value X from Z. So I know Z bar. What is Z bar? Z bar is the long term average of Z. Because stationarity, I assume Z bar has stabilized. So Z bar is invariant in time. So Z tilde is equal to Z minus Z bar. That is an anomaly of Z with respect to the long term average Z bar. Similarly, let X tilde be X minus X bar. I know X bar because I have computed D with it. I don't know X. X is the one I want to be able to determine. But instead of computing X, I am going to compute X tilde. So if computing X is equal to computing X tilde, because if I know X tilde, I can add X tilde to X bar to get X. So I am going to work with anomalies. Let Z bar be the observation anomaly on a new day. Let X bar, did I say bar? I'm sorry. Z tilde be the observation anomaly on a given new day. Let X tilde be the corresponding induced anomaly in the grid. My job is to be able to optimally determine X tilde from Z tilde knowing CND. Please understand, the background X bar is known. We can recover X once X tilde is computed. So we are simply going to concentrate on computing the X tilde anomaly. So what is the optimal interpolation approach? Please understand, this is one of the earliest known methods in predictive science. The basic idea of this optimal interpolation is to express the analysis increment. What is the analysis increment? X minus X bar. So X tilde I, what is X tilde I? X tilde I is the new increment at the location at the grid point I that is to be gleaned from the new observation. I am assuming I can express my Xi tilde as the linear combinations of the observation increments z tilde. So let me I want to make sure my z tilde is not, that's right, that's z tilde. So z tilde is the vector of observation increments. I am going to compute location by location, grid location by grid location. I is the ith grid location. Xi tilde is what I want to compute. Now I have to concoct a model that relates the known to the unknowns. Xi tilde is not known, z tilde is known. So I am going to confine my attention to the class of recovery process, to a class of estimators where xi tilde is expressed simply as the linear combinations of the elements of z tilde. Are you with me? So I want you to think about that. That's it. So what is that we are going to do? If I am going to have a linear combination, I need to have the weights. So let W be the vector of weights that are going to be used in the linear combination. W's are unknown weight vector. So given this philosophy of connecting the known to the unknown, let the unknown be the linear combination of the knowns. So I could express this as W transpose Z tilde. Therefore under what condition X tilde I will be optimal? It will be optimal under the optimal choice of W vector. So the whole problem now reduces to finding an optimal vector, optimal weight vector W. Optimal in what sense? Again we come back to least squares. Both Kolmogorov and Wiener independently in 1941 they were separated geographically, they did not talk to each other, but they had come up with very similar ideas. So the mathematical problem now reduces to the following: find a vector W belonging to Rm that minimizes the mean square error between the value of the increment at the ith grid from the linear combinations, because underlying quantities are all naturally random. I have to take the expected value. So the objective function here is the mean of the square of the error. So xi is the ith component of the analysis increment vector at a given time. So all these things are done at a given time. If you are interested in various times, I have to repeat it at a given time. So with a loss of generality I am assuming k is fixed, k the time is fixed. So z tilde is the vector, z tilde I is the ith component of the observation increment. For convenience we have suppressed the time index because we have fixed the time. This is an analysis being done at a given time. So if you have a subroutine that can do this, I can repeatedly use this for various times. I hope the formulation of the problem is clear now. Look at this now. I am falling back to least squares, but I am falling back to least squares not with respect to static model or dynamic model, but based on correlation structure, cross correlation structure, stationarity assumption, and so on. F of W can be now written as this because it is like a minus b whole square. Expectation operator I can pull it into each of the term. Expectation of the sum is sum of the expectations. The first term is the variance of xi's expectation of the square of xi tilde is the variance. Expected value of xi tilde z tilde transpose, it is essentially the ith row of D. So that is denoted by di star. Please remember D is the cross covariance between the grid and the observation location. So I know every grid point will be related to every observation locations. So here I would like to talk about a particular difference between Kurtzman scheme and other scheme. In Kurtzman scheme, what is that we assumed? Given point, the number of observation stations that can affect the given grid point are those that are lying within the radius of influence d. That came in 1950s, mid 50s. In Wiener's time in early 40s, 41, 42, they did not restrict the influence of one and the other. They assumed everybody is going to influence everybody, but they were measuring the influence through correlation and cross correlation. So the ith grid point has a cross correlation with every observation station, and that is given by the ith row di star. So this now becomes 2 times di star w. Now I would like to go back to the w is a column vector. I want you to understand w is a column vector, di star is a row vector. So di star w, I am sorry, di star w, that is an inner product. It is a scalar because one is the row, another is a column vector. Now that last term is essentially W transpose CW. You remember C, the correlation among observational locations? Now look at this equation 9. Equation 9 relates to the ith row vector of D, the entire matrix C, and the variance of the field variable at the ith grid point. All of them are known. What is the only thing that is not known? W. Now please also realize this f of w in 9 is a quadratic form. So what is the mathematical problem? Pick w such that this quadratic form is the minimum. How many times we have minimized quadratic forms in this class? Million times. So one is a quadratic variable, another is a linear variable, another is a constant. So computing the gradient of f of w in 9, I am not going to do the arithmetic. I very strongly encourage you to apply the principles from multivariate calculus that we have talked about. The gradient is given by 10, the Hessian is given by 2c. We have already assumed c is SPD, so Hessian is SPD. So if I equate the gradient to 0, given that the Hessian is SPD, it must be a minimum because the function, quadratic function is a convex function, is a unique minimum. So the solution of 10 is given by 12. Let us look at that now. C is the matrix. C is a m by m matrix. W is a vector which is m by 1 vector. That must be equal to di star transpose. Please remember, di star transpose is the ith row. Let us go back to now D. D is a n by m matrix. Therefore in the matrix D, if I consider the ith row is the m vector because this is m. Therefore di star is the ith row, di star transpose is the m column vector. So this is of the form Ax is equal to B, where A is an SPD. Now do you remember, this is a linear system with symmetric positive different matrix. I want to solve this. How many different methods we have seen? I can solve this by Cholesky, I can solve this by QR, I can solve this by SVD, I can solve this by iterative schemes such as Gauss-Seidel. There are ever so many methods. I can also solve this by gradient method. I can also solve this by conjugate gradient method. Now you can see the power of the mathematical tools that we have already developed. That is the key. We are looking at the foundational aspects of algorithms to do data assimilation, no matter what variety of assimilation process we are involved in. Please remember, this idea is extremely different from any of the ones we have already seen, yet the tools we have developed are very helpful. Computing the quadratic form, computing the gradient, Hessian, minimizing the quadratic form, solving the resulting equation by matrix methods, by direct optimization methods. Those are all tools in your toolbox. In fact, I would like to remind all of you there is a famous saying, If hammer is the tool, if hammer is the only tool you have, every job looks like a nail. I want all of you to write this down and put it in your study. If you have only one tool and that tool happens to be hammer, what is that you can do with a hammer? You can only hit. So the famous proverb is, if hammer is the only tool you have, every job looks like a nail. You can only hit the nail. So what you cannot do depends on what you don't know or what you don't have. So larger your toolbox, the better it is. Now please understand, our toolbox has been filled with tools, rich tools that can be used in solving problems. Therefore 12 is a solution of a symmetric partial differential system. I can solve this by one of several methods. I would like the reader to indulge in this process and convince oneself that I can solve 12 by one of many methods. But now by repeating this process for each I, we can obtain analysis increment over the entire grid. But now look at this now. If I want to solve this, so for every I, the left hand side remains the same, only the right hand side changes. Are you with me? So we are going to have a collection of n linear system with the same matrix C, but the right hand side is different. What does it mean? If you compute the Cholesky factor for C once, I can use it repeatedly for every solution for various grid points. So that is a computational advantage. So we can solve this efficiently by using Cholesky decomposition of C once and repeatedly using the Cholesky factor to solve the grid variables at each of the n locations. This method has come to be called optimal interpolation. In the area of geophysics, there is a method called Kriging. I am sure many of you who are in geophysical sciences could have heard of that. Kriging is a method, essentially an optimal interpolation method. So Wiener's method have been applied to many different fields of activity. It has been applied under the camouflage of very many different names. Kriging is one such name that has been applied in geology and geophysics. Kriging is, if you look at the mathematics of it, Kriging is essentially Wiener-Kolmogov's optimal interpolation. The person who popularized the application of optimal interpolation, especially in atmospheric as well as oceanographic sciences, is the Russian scientist Lev Gandin. Gandin has published a book that is totally devoted to application of OI to solve several different problems of interest in climatology, oceanography, atmospheric sciences and so on. And I would strongly recommend the reader to take a look at this extremely good book by Lev Gandin. Now I am going to talk very quickly about the extensions. Case 2, noisy observations. In practice, observations are noisy. Noise is unavoidable. Therefore my observation Z is equal to Z bar is the mean, Z tilde as the anomaly. Until now we had only Z is equal to Z bar plus Z tilde. Now we have a new guy coming into the table, coming into the game, and that is V. V I am going to assume is Gaussian, R is SPD. I am also going to assume that the natural variability in Z and the observation noise are uncorrelated. That makes sense. The climate does not care for the instrument you use to measure. So V essentially comes from the measuring process. The measuring process is not, or it does not affect the natural variability of a climatic system. So the cross correlation between the natural variability of field variable interest and the observations are 0. In this case I can now compute the covariance of since we have discussed many of these things in detail, I am going to hit all the major points. So Z bar is Z tilde is given by this. So its covariance is Z tilde times Z tilde transpose. There are 4 terms. The cross terms vanish because there is no covariance between V and Z tilde. So we are left with covariance of Z tilde is C plus R. Now look at this now. What is the role of R? R increases the covariance. Earlier R was 0 because there is no observation noise, observations are perfect. This is the only difference, rest of it all the same. So wherever there was C, you replace C by C plus R, solve the problem. So again, it is reasonable to assume the analysis increment is correlated with the it is reasonable to assume that the analysis increment is uncorrelated with observation noise. Sorry. It's uncorrelated, and that is described by this. So I can define D. D is given by the similar formula. I have an FW, which is the weight vector. So the whole thing, I am simply again assuming the grid analysis increment is the linear combination of the observation analysis increment. Now, how good this is the linearity assumption, you can change that, but to get the ball started, Kolmogorov and Wiener assumed that the given increment can be expressed as a linear combination of the observed one. So you can probably, in a given situation, you can try other combinations of the dependence of x tilde and z delta and do the analysis. But the trouble is, if the instant you bring in nonlinearity, that's going to be computational trouble. So you have to worry about, is the trouble worth it? If you take the trouble and spend more money to solve the nonlinear problem, is it going to improve your prediction estimates? So these are all open questions. I'm not going to indulge in all other possibilities. It is simply to provide you a new way of thinking about prediction. So if you consider FFW, and again I have given all the details, I would leave this as an exercise. So this is the quadratic form. You compute the gradient, you compute the Hessian. You can see wherever there was C, C is replaced by C plus R. So except for that difference, there is not much. So the optimal W is now obtained as a solution of this. If you set R is equal to 0, I get the previous equation. So so what is the fundamental idea? Knowing the correlation structure of the field variable, we can this is lowercase, we can easily lift the information from the observation network to the computational grid. That's the essence of this discussion. This module is contained in chapter 19, where we have discussed this at greater length, book by Lewis Lakshmi Rahandal 2006. With this I hope we have given you an opportunity to develop an appreciation for another way of thinking about prediction, creating analysis, how to transfer the new information and combine it with the old information. I want to talk about that part a little bit. Z, the new observation, that is the new information. C and D, old information. So in some sense you can think C and D as an equivalent of prior. Z has a new information. Maybe base is creeping in very quickly here. There are two pieces of information, I am trying to combine them. I am trying to combine them so as to minimize the error in the estimate. Least squares comes in, creeps in secretly. So base comes in secretly, least squares comes in explicitly. You can see the commonality between various techniques, even though the basic assumptions with which these techniques are developed are totally different. With that, we conclude our discussion on the optimal interpolation techniques. Thank you.